have to discuss today and tomorrow?
So today we left 3, and tomorrow.
No, let's finish. No, let's finish today. Sorry, I didn't know
Okay.
that you have 2 more for today. Yeah.
3 more. All right. Then Felix, can you come? Are you there?
Yeah, 1 moment. Yeah, I will do it quickly. Yeah.
Yeah.
No, you don't have to.
Good.
I mean,
I will share my screen. I think then it's easier for us.
Yeah.
So, do you see my screen?
Yes.
Yes. So my investigation was how temperature is affecting the water spectra, because I think this is really a critical aspect, that the temperature in the laboratory and of the measurement device and of the sample is also affecting the spectra we are recording. And this is a difficult thing to figure out, because measuring temperature of a material is not a trivial thing. And this is just a tiny investigation and study about this phenomena and how to deal with it. So I used a data set from Romania's lab that contained water spectra recorded at different temperatures ranging from about 20 to 70 degrees. And 3 different types of water were analyzed: molecule water, tap water, and distilled water. And what I was using, what I was doing was I tried to figure out which regions of the water spectrum are most disturbed or changed by the temperature. And based on my analysis, I could show that especially 3 regions are important. I found out that the 744 nanometers, the 759 nanometer, and the 803 nanometer region is important to determine the temperature of the water. So what I was doing, I performed a multivariate regression and derived an equation that could predict the temperature of the water sample based on the spectral properties. And this is the application of the equation. So normally, one can use just a temperature sensor attached to the vessel to determine the temperature of the probe. And this is the measurement done for many consecutive measurements, 0 to 51. And you can see that each time I'm changing the sample, there's a little bit difference of the temperature of the measurement vessel. So this has an effect, but it's not really actually the temperature of the substance I'm measuring. It's not the temperature inside the sample. But with the spectrally derived temperature approach, it is in principle possible to determine the actual temperature of the substance. And this looks like this then. So you can see there's quite a lot of change happening between the different measurements. These are always 3 consecutive measurements. And then I changed the probe, used a different water and so on. But I assumed normally that the temperature would be more or less stable. But this is not the case. There are really these discrete changes, baseline changes of the temperature. And of course, this needs to be incorporated in the modeling to make sure that the temperature variation is not modeled and only the independent spectral features are used by the model to determine then, for example, different concentrations of substances in the water and so on. So this is my point and my work, which I will also continue to do to figure out how to measure the temperature of the sample and to use this information then in the processing and analysis. Thank you.
Thank you, Felix. You really bring out a nice point, like Herbert Kaur was interested that we need to correct what we call, we need to correct something that actually bothers us, but I must say that the temperature is a property which arises from this system. So I'm not sure what when we measure the temperature. I mean, if you put salts in some salts in the water, for example, they would heat up water, but they would actually the heat in the temperature is a result of restructuring of water caused by salt and so on. So I'm not sure that the environmental temperature is the thing that only influences what we measure as temperature.
That is a good point. So it's
Yes.
most probably a combination of different sources of temperature change. And the most obvious one is a change in the environmental temperature, maybe also due to the spectrometer, that it's getting hotter or cooler in some different phases. But the other thing is the most interesting thing, the temperature change happening inside the sample due to some chemical reactions, for example. Yeah, good point. But it's another aspect to disentangle maybe these two things.
Or we may have to learn to live with that, like Professor Schau is using, I guess. Sorry, we have one question. So do you see Pierre's question in the chat?
Yes.
Yeah, I will have to look at the chat. Chat disappeared, one moment. So KTAT is altered as one probes the water samples. This is another thing, yeah, of course, if we are irradiating the water sample with electromagnetic radiation, i.e. infrared light, we are changing also thermodynamically the water and the probe, which can also cause an increase in the temperature. But in my measurements, I looked at this with the 3 consecutive measurements, as you can see in the figure, and there was not quite a lot of change happening when repeatedly scanning the same sample. So I would say this effect is not that dramatic.
Now I have to come in. So with water, when you work with water, there are not much changes is exactly what we look at. We look at very small changes. And this is what matters. And this is what makes lots of information. This is the information, small changes. Now, 3 consecutive spectra bring a linear increase of the temperature. When you increase consecutives, when you have 5, 10, then light starts organizing the water and starts making water structures. So you get absolutely nonlinear system, and it becomes very interesting. So, and I had a student working on that recently. He could not believe that the temperature of the sample started decreasing. And it does not decrease because of some other reasons. It decreases because light organizes, makes water structures, and water starts behaving like an ice, and the temperature decreases. So we have few things overlapping. Number one, temperature is the strongest perturber of the water. Or in other words, as you grasp it, you know it. Temperature, water is most sensitive to temperature. So, and the best thermometer, if we can think of, might be water-light interaction. But at the same time, Professor Schau uses how each system changes the temperature in order to measure some other analytes inside. So, for example, if you have molecule water and then you have merc molecule, or you have filtered pure water, these waters will have different spectral pattern, and they will get influenced differently from the temperature. So it is a very interesting topic.
Yes. Maybe we can't really make things static and measure. It's a Heisenberg's principle.
No, but the way Felix analyzed the data is very interesting. So I mean, all the data that we need, lots of data, lots of systems, temperature changes, and all these data analytical approaches to deal with, to predict it. What do you think, Felix? Yeah, the data analysis is the key, I think.
So Felix, Zoltan Kovac would like to ask something.
If I may, I just want to add a little bit of experience. When Professor Chenko started to say that one student of her is working on it, first I thought she's talking about me, when I realized, no, I'm not her student anymore. But I wish I would.
But you have lots of experience with this.
Yes, and if I can share my screen for a second, I don't want to take too much of your time. This time probably I succeed. Do you see my screen?
Yes.
And your straight lines, Zoltan.
Yes, that's great. So we also did this kind of studies, and I just confirm what Professor Chenko said. Of course, near infrared is the best thermometer. We purchased a very precise thermometer which could display the second digit even after the 0. And then we started to apply consecutive scanning. And in this case, our benchtop spectrophotometer, the XDS, was equipped with a thermobath. So we had continuous circulation of hot water. And beside that, then we started to record the temperature. And when we introduced the first scan, the second scan, the third scan, and so on, we could see pseudo-linear, I wouldn't say it's linear, pseudo-linear trend. And we continued this up to 15 scans. And after some point, what we realized, it got to a kind of equilibrium. And then it was above the line, below the line, something like that.
Yes.
So certainly there are several phenomena fighting here, including the temperature regulation, including the power of light, and who knows what else. I just wanted to add this experience here. I don't know if it helps.
Fantastic. I know.
Thank you.
I know what you mean.
Yes.
That's a good comment. Yeah, I think it's a combination of thermal effects and non-thermal effects.
Yes.
So at the end, we have to somehow determine the impact of these non-thermal and thermal effects coming from the measurement by itself.
Yes.
How they are affecting the whole measurements. So it gets really complicated and messy at the end. But we have to deal with it.
Yeah, and the reference methods. Yeah, the thermometer that gives you, well, we pay lots of money for 0.003 digits, but who knows how accurate is that one thermometer?
Pierre has a very nice point, and at this, and I mean, comment to your comment. So now I'm really looking forward. I actually so don't understand quantum theory and so on, and I'm totally confused with all that. So I'm really looking forward, Pierre, for example, or Felix, if you can, to solve.
No, that's a very good question that Pierre is asking, and he's talking quantum all the time. What I have to tell you is that with this particular experiment that Zoltan did and the paper that we wrote, Paulo is the first author. We proved that water is fractal. We saw the coherent domains in water, but we saw also that there is incoherent part of the water. So, and that incoherent part is exactly around the isospecific point of water. And there is a lot that we don't understand. That from now on, I mean, so that's why we're doing what we're doing now. Yeah, but I am aware of what you are thinking about.
And I think, by the way, tomorrow's morning speaker from the South America, the second speaker, is going to be mentioning this also. Jorge Vance, he's also got interesting results about temperature. So we'll see that. Stay tuned for the next
and
morning
if I may add 2 more sentences, you mentioned Paulo. Of course, we wanted to measure this, and with Paulo, we slightly modified the spectrophotometers. Fortunately, Professor Chenko was not there. No, I'm joking. But we really tried to replace the cuvette with a known object, some alumina plates, so we can calculate all the parameters. And try to measure the power of light, but it was in a very tiny level, so we didn't succeed. So this is what I mean, that we would need more experiment and more deep discussions to really figure out how we could really separate these effects.
And today, in some of the discussions, I think Jelena pointed out that we could, it is a very important, I think, we haven't done anything, somebody has to do it. It is very important if we use coherent source of light, if we use laser at different wavelengths, or we use a halogen lamp, or we use LEDs, or and that also is very important, because then we bring up the coherence issue. The coherence of the light source and the coherence of the system. So interesting, very interesting.
Things to do.
Yeah. Okay.
A great suggestion for the next generation